Welcome to a video lecture that follows along with the video from Walter Lewin. This talks about the Snell's Law and the refraction of light. Follows along in sections 26.1 and 26.2. The index of refraction is a constant for every different material. And this is it's a number basically that is describes the ability of light moving through that object. It needs to be transparent so that light can travel through it, but it's really relates the speed of light within that medium or within that material to the speed of light within just a vacuum. Index of refraction, once again, is just a number. Here are some sample indexes of refraction, and these have been, there's a way they've been calculated out and actually measured also. And for example, the speed of light within glass is actually moves at 2/3 the speed of light within a vacuum. So speed of light within a vacuum is 3 times 10 to the 8th, or roughly right there. And for a glass, the index of refraction is 1.5, so we can actually determine the speed of light within glass. Now for air is pretty close to just the same exact speed of light as within a vacuum, and for most intensive purposes, we'll just use 1 for the index of refraction for air. When light hits the point between two different surfaces, that interface right there, there is what we call, there's a bending of light in that surface depending on the index of refraction. First off, there's going to be some percentage of the light is going to be reflected back. This also depends on the difference in index of refraction between the two surfaces. Second, there's going to be some part of that light that's refracted and passes through but bends. This depends on Snell's law. And if the index of refraction is higher in the second surface, the refracted ray will move towards the normal. Keep in mind, this is the angle between the ray and the normal, which is the perpendicular to the surface. And if the index of refraction in the second surface, where the light is moving to, is lower than the index of refraction in the first surface, the ray of light will move away from the normal, further away from the normal. Those are some key ideas there. I'd make sure to go back and fully understand what I'm trying to say, and look at the diagram. Snell's law occurs because as a wave moves up from one medium to another, as we say, it bends. This is because the speed changes, and it actually has to do with the fact that light is it's both a wave and a particle, and this has to do with the wave nature of light. As it moves from one medium to the other, the horizontal component of the velocity does not change, but the vertical component of the velocity does change. This means that the overall wavelength will become shorter or shorter or longer, depending on whether it's going from a surface of high index of refraction to a low index of refraction, or the other way around. And from this, we get the idea of Snell's law, saying that N1, this is the index of refraction for medium 1, times the sine of the angle, and this is the incident angle for medium 1, and that's respect to the normal, is equal to the index of refraction for the second medium times the angle with respect to the normal, once again, the sine of that angle in medium 2. Within water, light is reflected off some object, and it comes out the surface of that out of the water. And when it moves out of the surface of the water, it actually bends or refracts, as we say. And this gives the image the idea that it is at a different point, or further away, deeper down, with respect to the actual water. Now, this is regardless of where you are located, because the horizontal component doesn't really change. It's really just the vertical component. All right, question number 1. What if a treasure chest, because everybody likes pirates, is sunk in water at an apparent depth of 6.4 meters? What is the actual depth? And for this, you need to know the index of refraction of water. You need to know the index of refraction of air. And you need to understand some geometric ideas here in that notice where the apparent depth of the trunk, where the position is located. What's the only thing that changes if you were to draw out similar triangles from that respect? What are the only ideas that change? Look in your book too. There may be some help in there. All right, questions number 2 and 3. If the light in the top picture, incident light in the top picture, is at an angle of 40 degrees, what is the angle of the refracted ray? And question number 3, if the incident light in the bottom picture is at an angle of 45 degrees, what is the angle of the refracted ray? Keep in mind that the second picture, the light is going from an area of high index of refraction to low index of refraction. So this is why it's moving away from the normal. Please make sure to put these answers in online, and I will see you tomorrow in class. Thank you very much.